Okay, so good morning everyone. So today we are going to look at another model of computation, namely branching programs. So branching programs are similar to circuits. It's another model of non-uniform computation. So where we can give inputs of a fixed length, and depending on the structure of the program, we expect the program to accept classes of functions. And then we'll look at connections between branching programs and some circuit classes. Okay, so that is going to be the agenda for today. So what is a branching program? So so the way we define a branching program is, so a branching program so it is a directed acyclic graph where every node has out degree 0 or 2. Okay. Nodes with out degree 2 are labeled with a variable, and nodes with out degree 0, so they are also called sinks, are labeled with the constants 0 or 1. Next, there is a designated source vertex. Okay, so we can call it as S. Okay, so basically what is a branching program? So we have a directed acyclic graph. Every node of out degree 2 is labeled with some variable from x1 to xn, some, let's say xi, and nodes with out degree 0 are labeled with constants 0 or 1. So now how does a branching program accept its input? So let's give it a name. So a branching program, let's say we call it P. So P accepts, okay, maybe I should say one more thing, a branching program P on n variables, because it is a non-uniform model of computation. Each program is for a fixed number of variables on n variables. Okay, is defined as follows. So P accepts x belonging to 0, 1 to the power n if okay, so before I say this, maybe I have to say one more thing. At out degree 2 nodes, the two outgoing edges are labeled 0 and 1. Okay, so this is the labeling. So for example, so we can have maybe a branching program that looks like this. So let's say this is some x1. I have maybe another x1. Let's say this is 0, 1, x2, x3, zero, 1, 0, 1, 0 and 1. Okay, so this is an example of a branching program. So now P accepts x belonging to 0, 1 to the power n if and let's say this is my source over here. There is a path from S to the or to a vertex labeled 1 by following edges as follows, or by say taking edges as follows. At a node xi, take the edge labeled 1 if the ith bit of x is 1, otherwise take the edge 0. Okay, so basically in a canonical manner you take the edges. So you start at the source vertex. Now suppose I consider an input x. So we have 3 variables over here. So let's say consider the input 1, 0, 1. Okay, so now I start at x. So x1 is 1, so I'll take 1. Now I come at x2. X2 is 0, so I take 0. X1 is 1, so I take 1 and I land at 0. Okay, so this input is not accepted. On the other hand, if I consider, let's say, another input, maybe y, which is equal to 1 1 1, x1 I take 1, then I reach x2, the second bit is 1, so I take a 1, at here also third bit is 1, I take a 1, I land at 1, so this is accepted. Okay. So this is how a branching program accepts or rejects an input. So now the question is, what is the power? How does this model of computation connect to whatever model of computations we have studied so far, that is circuits or Turing machines? So first of all, as I said, that this is a non-uniform model of computation, that is we have a branching program for a fixed input length. So the first theorem that I would state is actually more than a theorem, this is kind of folklore, and this is actually, it mostly follows from definitions with a little bit of observation, that is okay. So before I define this theorem, just a couple of more definitions. So the size of a branching program is the number of nodes in it. Okay, and we can define the class BP size, let's say S of n, as set of all languages L such that there exists a family of branching programs of size bounded by order S of n accepting L. So this is in the natural manner. So we have a language, it can have inputs of different lengths. So if I have a family of branching program, that is for each input length I have a different branching program, and their sizes, the size of each branching program in that family is bounded by order S of n, okay, such that for a fixed input length it accepts all strings that belongs to L and rejects everything that does not belong to L. Then we say that that language belongs to BP size of S of n. Again, this is the natural manner in defining them. So now I can state the theorem that branching programs of polynomial size. So BP size poly essentially means that any branching program whose size is polynomial. So another way to define it would be union over BP size of n to the power c for all c. Okay. So this is equal to what? L slash poly. Okay. So I'm not going to give the proof of this. I mean, the proof is sort of standard. I'll just maybe give a sketch or just hint towards the proof. So let's look at the forward direction. How does the forward direction happen? So given a branching program, how do you build a L slash poly machine? So basically you have to give a Turing machine for a fixed input length. How do you do it? Such that the space used by that machine is logarithmic in the space of the or the size of the program. So essentially what that machine would do, so the way you define the Turing machine is it would simulate. So think of that branching program as a DAG, right? So we have a DAG that is there. Now given an input, what do I have to do? Whenever I reach a node of the branching program, I look at the input and I decide which edge to take, whether to take the edge label 0 or to take the edge label 1, and I take that edge. And I continue doing this until and unless I reach the node that is labeled 0 or 1. Okay. So I just design an algorithm that exactly does this, and the space used by that algorithm will be logarithmic in the size of the branching program, because at any point. So basically I would be running let's say it's kind of a while loop. So while I don't reach a sync vertex, I would be keep on doing the following, that whenever I am at a vertex, I look at the input and I take the edge accordingly. Okay. So I would have to kind of store at any point in time what node of the branching program I am at, and that would take space that is logarithmic in the size of the program. Okay. So essentially the idea is that trace the branching program on a given input. Yeah. What about the reverse? So given let's say a log space machine, how do I get a branching program out of it? Whose size is at most exponential in the space used by that algorithm. Okay. So the machine, the log space machine, of course uses space that is log space. So I have to get a branching program that is polynomial in log space, or 2 to the power log, which is polynomial. Yeah, so essentially you look at the configuration graph of that machine. So you have this log space machine. So you look at the graph where, well, it's not exactly the configuration graph, because configuration graph is defined for a machine and an input. Here you don't well have an input as such. You have the machine. Now that log space machine, so look at the tape of that log space machine. Okay, so you have the input, and then you have some more space that is given to you, some workspace that is given to you, which is bounded by log space. Okay. Now at each step of that, how does that machine work? So at each step it looks at a input bit, it looks at maybe a bit in the workspace, and it decides to go, I mean it looks at the transition function and it makes a decision which state to go to and which way to move the head. Okay. So this thing can actually be represented using a branching program. So each configuration, for each configuration you will have a node of the branching program. Okay. So represent the so this is, I just put it in quotes because it's not exactly configuration graph, it's a little bit more general, as a branching program. Now at every node what do you do? So you take two choices. If that bit, if that input bit was 0, which node, which configuration, which node of the configuration graph you go to, and if that bit was 1, which node of the configuration graph you go to, and that is exactly the design of the branching program. Now the size of the branching program will be at most exponential in the number of, or the space used by the workspace of the log space machine, which is polynomial. Okay, or the size of the configuration graph, the total number of nodes in the configuration graph. So this is roughly the proof idea, and this, as I said, this is not something that is very non-trivial. This is kind of, it follows from the definition. Okay, so what do we have so far? So we have that, well, branching programs of polynomial size are sort of like log space computation. Now what about restricted forms? Okay, what if I restrict the branching program to something smaller? What kind of classes do they capture? Okay, so that is what we are going to study for the rest of today's lecture. So now let me define a restriction of branching program, namely bounded width branching programs. So for bounded width branching program, how do we define them? So we define a layered DAG. So from a DAG we define what is called a layered DAG. So a layered DAG is a DAG where the vertex set is partitioned say V0, V1 up to some V T into T, or well, T plus 1 actually, and each edge goes from a layer I to I plus 1. Okay, so each edge of the DAG goes from a layer I to a layer I plus 1, and this is a partition, which means that it the union of all these so these vertex sets are called layers. Okay, union of all these vertex sets gives me V, and they are disjoint. Okay, so they are pairwise disjoint, so no vertex belongs to more than one layer. Okay, so we have a layered DAG, and well, the width of a of the corresponding branching program is equal to maximum over the size of all the VI's over I. Okay. So now we have a concept of a width of a branching program. Okay. So suppose if the branching program corresponds to a layered DAG, and if I look at the maximum size of a layer in that layered DAG, that is the definition of the width of a branching program. So now we want to ask the question that, well, if I look at branching programs which have bounded width, what is their complexity? Okay, like how much is it restricted from the class L? Okay, so in particular, what we will be looking at today is basically branching programs of constant width. Okay, now how much? Okay, so we'll be considering so what is the power of branching programs of constant? So this is the question that we ask. Now let's just think about it. Okay, so when we have polynomial size, so when we have polynomial size, it can have polynomial width, polynomial. Okay, so length is something that I haven't defined, so I can define it over here. So the length of a branching program is the maximum path length from source to some sink. Okay, so in other words, it is actually bounded by T over here. Okay, because you cannot have a path of length more than T if you have a layered branching program. It can be less than T, but it cannot be certainly more than T. Okay, so now the question is that what is the power of constant width branching program? So now if you think about a constant width branching program, essentially at every layer it can only encode a constant number of information, a constant amount of information, right. So, it was not expected to be like something that is too powerful. Okay, in other words, if you look at functions such as for example that are computable in NC1. Okay, so for example, if I want to compare constant with branching program with the class NC1, so NC1 is the class of circuits of logarithmic depth. Well, NC1 was believed to be much more powerful than branching program, because in NC1 you can do things like multiplication, you can do things like majority and so on. But what is majority? Majority is basically you have n bits and you want to find out if it has more than n by 2 number of ones. Now, how do you, so basically you need a sort of count. Now, how can you count if you are only encoding some constant amount of information at every layer? Because in the next layer you have to kind of erase whatever you had earlier. Well, not exactly erase, but you don't you cannot carry it forward. Okay. So, this brings us to this famous result by Barrington, who showed that this intuition is actually false, and this was kind of well, yeah, I mean, this was kind of something that was not believed before he proved this theorem, that NC1 is exactly as powerful as constant with branching programs. Okay. So, theorem, let me call this as theorem 1. This was 85 or 86 probably, that let L be a language, L is accepted by a family of branching programs of bounded or constant width if and only if L is in NC1. When I say NC1, it is non-uniform NC1. Okay. So, of course, the forward direction is not very difficult to see, that if L is accepted by a family of I mean, it's accepted by a family of constant with branching programs, then L is in NC1. That way it can be shown is that, well, if I have let us say a branching program of length some L, okay, or length some, yeah, okay, length say L. Now, what I can do is that, and at each layer I only have constant number of vertices. Okay. Now, what I can do is that I can encode the computation that is happening in consecutive layers as a constant sized matrix. Okay. The way it is encoded is that, well, I have some the width is, let us say, some W. So, I have some D number of sorry, I have some W number of nodes over here, and I have another W number of nodes over here. Now, how many ways can you go from here to here, or how many functions are there from here to here? So, each node here can potentially go to any of the W nodes over here, right, and there are two choices. So, W into W, let us say some W square, and then I have W many different nodes over here. So, it is some constant, because W is a constant. So, I have some constant number of ways of going from here to here. So, this can be encoded as a matrix of constant size. Now, how many such layers I have? So, I have a total of L such layer. Okay. So, I can think of it as a product of these constant size matrices. Now, basically I have encoded the computation of a branching program, of a constant width branching program, as a product of I mean solving a product of constant sized matrices, L many constant sized matrices. Now this can be solved in NC1 by just some simple divide and conquer. So I group them into L by 2 matrices, I mean 2 L by 2 matrices, and then I just keep on doing this. So in depth log n, I would be coming to just product of 2 matrices, and that can, I mean, easily be done by a constant depth circuit. Okay. So yeah, so this is basically the proof of the forward direction, or I shouldn't say proof, but a sketch of the proof of the forward direction. This is the, you can actually, as homework, you can just formalize exactly what the NC1 construction would be, but this was something that was believed. But what about the reverse direction? So as I said, that functions which are there in NC1, so they can be so complex that it was kind of counterintuitive, or it was very it was not believed that there could be constant width branching programs for those functions. Okay. So how does the proof go in the reverse direction? So for the reverse direction, what we would do is we would show something that is even stronger in the sense that not just any constant, but if L is in NC1, then it can be recognized by families of branching program of width 5. Okay. So this constant is actually something that is quite small, okay, something as small as 5 in our case. And what we would do is we will show an even stronger result, that not only is any language in NC1, for any language in NC1 there is a family of branching program of width 5, but there is a family of a very special type of branching program, okay, namely permutation branching program. Okay. So next what I am going to do is I will define what a permutation branching program is, and then we will show that how any language L can be accepted by a permutation branching program. Okay. So any questions at this point? Okay. Okay. So let's look at first what is a permutation branching program. So we will consider branching program in the following form. Firstly, all layers have the same size, okay. In each layer, a fixed variable is represented at every node. And the third thing is that between layers I and I plus 1, the edges labeled 0 So let me give a notation to this, have the same size, say W. Okay. So edges labeled 0 form a permutation of W, and so does the edges labeled 1. Okay. So again, let's look at this with an example. So if I look at the branching program, so I have a fixed width now. Okay. So at every layer I have exactly W many vertices. Okay. Now every vertex in a given layer is labeled with the same variable. Okay. So we can ensure that as well. So let us say here all the vertices are labeled with x1, here all the vertices are labeled maybe with x3 and so on, and maybe you can have another layer also where the vertices are labeled with x3 and so on. And the third point is that if I look at all the edges that are labeled 0 between I and I plus 1, so let us say I have some 0 here, a 0 here, another 0 here, they form a permutation of W, okay, and so does the edges labeled 1. Okay. Similarly, for 1 also I will be getting a permutation. So this is what is a permutation branching program. So, and now I have a start node in the first layer. I have some edges that are labeled 1 and some edges that are labeled 0 in the last layer. So if I have a path from a start node to a node that is labeled 1 in the last layer on some input, I would accept it, otherwise not. Okay.